Hey, this is Physics Unit 3, video number 5. We are going to start talking about Newton's second law of motion. Newton's first law says that if no net force acts on an object, it will remain as it is either at rest or in uniform motion. The same idea could be stated differently. If no net force acts on an object, then its acceleration is 0. So acceleration is 0, we're talking about uniform motion. If it's at rest and the acceleration is 0, so what happens if a net force does act on an object? Newton's second law addresses this. The beginning statement of Newton's second law. We'll add more to it later. If a net force acts on an object, it will accelerate. Before we go further, we need to carefully define the concept of mass. There's really two definitions. There is inertial mass. It's a measure of the resistance of an object from being accelerated sideways. It's a measure of the inertia of an object. It's a measure of how hard it is to accelerate the object sideways. Inertial mass is things like hitting a football player and getting them to move backwards, or starting a car from rest at a stop sign, or if you're driving a pickup truck, coming to the stop at a stop sign. These are all measures of inertia. Everything has a certain inertial mass. Then there's gravitational mass, and this is a measure of the resistance of an object to being accelerated upward. This is really a measure of how hard it is to lift an object. If you were difficult to push sideways, as in you have a large inertial mass, then you are also probably difficult to lift. So the values of these two masses are the same. From now on, we'll just talk about them together and refer to either one as mass. This is the layman's definition of mass. This is the Unit 1, Chem 1 definition. Mass is the amount of matter in an object. The amount of matter in an object. Here's a very important idea. Mass and weight are not the same thing. They are different. Mass is a measure of how much matter there is. Mass is a scalar. Remember, we talked about scalars in an earlier unit. A scalar has magnitude but does not have direction. Weight is a measure of the force of gravity pulling down on an object. Weight is a vector. It's the force of gravity pulling down on an object. So it has both magnitude and direction. Now you may say that if a person's mass is greater, then the person's weight is greater. And that's true if some conditions here. If we're both standing on the earth and my mass is twice yours, then my weight is twice yours. So yes. But if I went to the moon and you stayed here, my mass would still be twice yours. But my weight would be 1/3 of yours, because the moon's gravity is about 1/6. So I weigh about 180 pounds. If I were on the moon, I would weigh 30. So if I weighed 180 pounds, that means that my weight is twice yours. You weigh 90 pounds. So I'm on the moon weighing 30. You're on Earth weighing 90. My weight is 1/3 of yours. Mass never changes from planet to planet. If I go to the moon, my mass is the same. If I went to Mars, my mass is the same. If I went to some other larger planet, my mass is the same. Weight is the value that changes. And that depends on what planet you're standing on. The concept of mass is very important in studying Newton's laws of motion. Back to our unfinished version of Newton's second law. If a net force acts on an object, it will accelerate. That's true, but it depends on two things. First off, it depends on the amount of net force applied. So let's take a look at this. So here's a surface, here's an object. It has a mass of m. I'm applying, say, this much of, this means net force, F net force. Adding this amount of net force to this mass, I get acceleration, and that's what happens. Well, let's look at a couple other scenarios. So we have the same surface, we have the same object, mass is the same. This time, I am going to add twice the amount of net force. So twice the force this time that I did last time. What do we expect with the acceleration? If I push something with twice as much force, I expect it to accelerate twice as much. Or another third scenario, same object, same mass. This time I'm pushing it with 3 times the force. What do I expect the acceleration to be? 3 times the acceleration. So it depends on, first off, how much force did I apply to it? The second thing that it depends on is the mass of the object. So here's our scenario 1 again. So here's my box, my object with mass m. I am adding this amount of net force, and it accelerates by this much. So same scenario that we had here. This time we're going to keep the force constant, but the mass of the object is going to increase. So here, draw a larger object and say that it has twice the mass. If I add the same amount of force as last time on an object that has twice the mass, we would expect it to accelerate less, and we would end up with 1/2 of the acceleration. Or if we add the same force to an object that is 3 times the mass, same amount of force here. Same force on triple the mass, we're probably going to expect 1/3 the amount of the acceleration. So adding more net force to an object accelerates it more. Increasing the mass of the object means it accelerates less. So the acceleration varies directly as the amount of net force applied. Net force increases, acceleration increases. That's a direct relationship, direct variation. And the amount of net force, so the acceleration varies inversely as the mass of the object. In symbols, we have two relationships. Acceleration is proportionality constant, directly proportional to the net force being applied. And we have acceleration is inversely proportional, here's a constant, inversely proportional to the mass of the object. And so if we were to put these two together, acceleration equals, here's our K for the constant, net force divided by mass. What about the value of K? We can't use this formula unless we know the value of K. In math class, we find the value of K by substituting in values for all the other variables. So let's do an experiment to find some values. Let's say we are going to accelerate a mass of 1 kilogram at a rate of 1 meter per second squared. To do this, a force of 1 unit is required. It would be nice if the new unit of force came out to be a nice value. Let's make it come out to being a nice value by defining a new unit of force. We define the unit of force called the Newton, for Sir Isaac Newton, to be just the right amount so that 1 Newton of force will accelerate 1 kilogram of mass at a rate of 1 meter per second per second. So that makes K equal 1, which makes our formula, acceleration is the net force divided by the mass. Another one that you'll see all the time in physics, rearranging this formula, says the net force is equal to mass times acceleration. F equals ma. So now let's state Newton's second law of motion in its entirety. If a net force acts on an object, it will accelerate. The acceleration varies directly with the net force and inversely with the mass. The acceleration is in the direction of the net force, which makes our formula, acceleration, which is a vector, acceleration has direction, equal to net force. Net force is a vector. Forces have both magnitude and direction. And inversely proportional to the mass. Mass is a scalar. Scalar does not have direction. Acceleration is in the direction of the net force.